Have you ever wondered what powers our planet? We see volcanoes erupting, continents drifting, and feel the protection of a magnetic field shielding us from solar winds. We're often told this is all thanks to a simple, hot iron core. But what if the truth is far more explosive? What if, deep beneath our feet, lies a colossal, naturally occurring nuclear reactor? It sounds like science fiction, but it's a genuine scientific hypothesis. And today, we're diving deep into the theory of the Georeactor. Let's start with a mind-blowing fact. Nature beat us to nuclear power by about 2 billion years. In 1972, in a place called Oklo in Gabon, Africa, scientists were analyzing uranium ore and found something astonishing. The concentration of a specific isotope, uranium-235, was lower than it should be. This wasn't a measurement error. It was evidence that the uranium had already undergone nuclear fission. They had discovered a natural nuclear reactor. Here's how it happened. About 2 billion years ago, the conditions were perfect. The concentration of fissile uranium-235 was much higher than it is today, roughly 3%. Groundwater seeped into the uranium deposit, acting as a moderator to slow down neutrons, which is crucial for a chain reaction. The water would heat up, turn to steam, and temporarily stop the reaction. As it cooled and condensed, the process would start all over again. These Oklo reactors operated in cycles for hundreds of thousands of years, generating energy equivalent to a small power plant. This isn't a theory, it's a proven fact. Nature built its own nuclear reactors. So, if it happened in the crust, could something similar, but on a much grander scale, be happening in the very center of our planet? This is the core of the Georeactor hypothesis, proposed by scientist J. Marvin Herndon. The standard model of Earth's core says its heat is left over from the planet's formation and from the slow decay of radioactive elements scattered throughout the mantle. But this model has some gaps. For instance, it struggles to fully explain the sheer amount of heat and the exact mechanism that powers our planet's magnetic field. The Georeactor theory offers a radical alternative. It suggests that a significant amount of uranium and other heavy radioactive elements, due to their immense density, sank to the very center of the planet during its formation. Over time, they could have accumulated into a critical mass, igniting a self-sustaining nuclear fission reaction. We're talking about a sphere of fissioning elements, potentially several kilometers across, acting as the Earth's primary engine. What's the evidence for this incredible idea? Well, it's indirect, but it's compelling. One of the biggest pieces of evidence comes from something called helium-3. When it produces various byproducts, including different isotopes of helium. The standard model has a hard time explaining the unusually high ratio of helium-3 to helium-4 that we see venting from the Earth's mantle, particularly in places like Hawaii and Iceland. The decay of elements in the mantle produces mostly helium-4, but nuclear fission. Then there's the Earth's magnetic field. We know it's generated by the movement of molten iron in the outer core of the geodynamo. But what keeps the iron churning? The standard model relies on thermal and compositional convection, which is a bit like a pot of water simmering on a stove. The Georeactor hypothesis provides a more powerful and concentrated heat source right at the center. This intense, localized heating could drive convection much more vigorously and consistently, providing a robust and long-lasting engine for our magnetic field. It might even help explain why the magnetic field sometimes flips its polarity. Bursts of activity or changes in the reactor's output could destabilize the dynamo, triggering a reversal. But of course, not everyone is convinced. The Georeactor hypothesis is definitely outside the mainstream. Many geophysicists argue that if a reactor existed, we should be able to detect it. How? Through its nuclear fission produces a flood of tiny, almost massless particles called they barely interact with matter, so they can travel straight from the Earth's core out into space. We have detectors around the world, like the Kameliende experiment in Japan, specifically designed to catch these elusive particles. So, have they found the Georeactor's signature? Well, not yet. The detectors have confirmed the antineutrinos produced by radioactive decay in the crust and mantle, which is a major discovery in itself. But they haven't detected the massive, high-energy signal that a powerful core reactor would produce. Proponents of the theory argue that perhaps the reactor is smaller or operates at a lower power than initially predicted, making its signal harder to distinguish from the background noise. Or maybe the uranium has been mostly used up, and the reactor is now running on bred plutonium, which produces lower energy antineutrinos that our current detectors aren't sensitive enough to find. The debate is far from over. Another major counterargument is chemistry. Skeptics question whether uranium would really behave the way the theory suggests under the immense pressures and temperatures of the core. Would it really separate out and concentrate? Or would it dissolve and mix with the surrounding ion? The physics of materials under such extreme conditions is incredibly complex and still not fully understood. We can't exactly take a sample from the core, so scientists have to rely on hypershore experiments and computer simulations, which have produced conflicting results. So, where does that leave us? We have a fascinating theory that elegantly solves some of geology's biggest puzzles. On the other hand, the lack of a definitive smoking gun signal, like a blast of high-energy antineutrinos, means it remains a speculative, though brilliant, idea. The quest to understand our planet's inner workings is one of the greatest detective stories in science. Whether Earth is powered by the slow fizz of remnant heat and widespread decay or by a roaring nuclear furnace at its heart, the truth is still waiting to be fully uncovered. The existence of the Oklo natural reactors proves that nature is capable of incredible things. It forces us to keep an open mind and to question our assumptions. Future experiments with more sensitive detectors might one day give us a definitive answer. For now, the mystery of the Georeactor remains, a powerful reminder of how much we still have to learn about the planet right beneath our feet. What do you think? Could our world be a giant nuclear reactor? Let me know your thoughts in the comments below. Thanks for watching, and if you enjoyed this journey to the center of the Earth, don't forget to like, subscribe, and hit that bell so you don't miss our next exploration into the mysteries of the universe.